Hi, I'm Francis, and today we'll be talking about thermal optimization of laser powder bed fusion using deep reinforcement learning. So laser powder bed fusion is a subdivision of additive manufacturing, where a substrate powder bed, typically metal alloy, is melted in specific areas by a laser to form the two-dimensional cross-section of a given part. And this enables the construction of complex three-dimensional parts that aren't always feasible with conventional manufacturing methods. On the other hand, however, it is likely to form defects because of, for instance, inconsistencies in melt pool depth or overheating in certain parts of the domain. So we are trying to use deep reinforcement learning to derive a control policy to dynamically adjust the process parameters to reduce the occurrence of temperature-related defects. So generally in deep reinforcement learning, an agent selects an action based on the current state, given a policy which maps each state to a specific action. This action is then deployed in the environment, and influence that this action has on the environment is quantified by the reward. So the policy is then updated based on this reward with the end goal of maximizing the observed reward, ideally by selecting the correct action in each state during the episode. So the state is defined as the temperature distribution surrounding the laser in 3 dimensions, so x, y, yc, and xz planes. The policy is a neural network, and the reward function penalizes deviations from the target melt depth. The control action specifies the velocity of the laser between 2 predefined points in the scan path. So essentially, the process parameter that's being varied here is the velocity of the laser. And PPO, or proximal policy optimization, is used to augment the policy network, and it improves convergence by limiting the maximum size of the update to the policy network. So since RL is relatively sample heavy, we abstract the physics of laser powder bed fusion to just the continuum temperature distribution surrounding the laser. And this is modeled using the Gear model, which is generated by using Green's function to solve the general heat conduction partial differential equation. So we implement a method introduced by Wolfer et al. Called the repeated use of stored line solutions, which decreases the computational expense associated with this process by storing analytical solutions in memory and reusing them whenever the same process parameters and delta t is observed in the future. So this removes the necessity to resolve the entire domain at each time step. So in this method, in general, to advance the solution by some time delta t, we apply Gaussian convolution or Gaussian blur to the solution at time t minus delta t to approximate the heat diffusion far away from the laser. And the Eager model is solved for time delta t, or if it's been counted before in a previous case for the same process parameters and same delta t, we simply just reuse that solution, and we superimpose it to the solution at time t minus delta t after the diffusion operation has been applied to generate the solution at time t. And in their paper, they show that this method is very similar to finite element results, but significantly reduces the computational expense associated with it. So to test this overall framework, it's optimized on 2 different scan paths, one where overheating is observed based on geometry, and one where overheating is observed based on the scan path itself. So the first is the horizontal cross-section path, which is commonly used in industry, where overheating may occur in the boundaries. And the second one is this concentric triangular path, where overheating may occur when changing the direction of the laser, or when heading toward the center of the domain, as heat builds up in the center of the domain. And in general, control is applied at every 50 micrometers of the scan path. So by examining the control policy, you can see the improvements that's made to the melt pool depth, as opposed to using a constant velocity for the entire case. So the velocity increases at specific points to reduce overheating. So in this case, in the horizontal cross-section case, we see increase in the velocity near the boundaries. And in a triangular case, we see increases the velocity whenever the laser changes direction, or as it heads more generally towards the center of the domain. And we see that when compared to the constant velocity case, the melt depth is much more stable, and there's spikes that are observed in the constant control case, and the constant velocity case are no longer observed in the controlled case. And it's exaggerated for the triangular case, where the large increase in melt pool depth that's seen towards the end of the trajectory is not seen in the controlled case. So in conclusion, we saw that DRL is able to drive control policy that reduces overheating by dynamically changing the velocity during the process. Thank you.